Hello, my name is Jakub, and I've been working on LVM and LVM-based projects for about 10 years now. Most recently, I'm doing GPU programming and GPU performance work in IREE, MLIR, LVM, at AMD. And I'm gonna introduce to you what ML models or like ML programs really look like, how we kind of implement them across the IREE and MLIR compiler stack. I'll give you a brief introduction to MLIR as a framework and also how we use it in IREE and how we structure our ML compilation flow. And at the end, I'm going to present some results and some ongoing work. So in case you haven't seen, your typical ML program will be a bunch of Python that calls into libraries like PyTorch, JAX, TensorFlow, and these expose very high-level ML operators. So you can see, for example, there are some functions like torch.matmul for matrix multiplication. There's a function to transpose tensors. There's a softmax function. And your most traditional implementations would then take these functions and have kernels that the Python will call into. So this will be a C kernel for CPU. This would be something like a CUDA kernel for GPU. And this works fine to some extent, except that now somebody has to implement all of these kernels. And the question is, do you really want to ship Python to your users that calls into kernels? This issue gets kind of exacerbated by if you want to support more than just one target device, you have to come up with kernel libraries for all of your supported devices. And as you kind of specialize towards more and more exotic hardware, you get generally better performance, but the harder it is to program. I like working on the GPU code gen specifically because it's still good in terms of the ease of use and also in terms of performance. And this is a broad range of devices because you can imagine you can have very fancy and expensive data center GPUs that people really want to get all of the performance out of. And you can also have very kind of diverse and weak GPUs in your like mobile devices like phones or tablets or other edge devices. And here, Vulkan is actually a very good solution for just this level of compatibility across consumer cards. If you are implementing ML kernels for C, you would see that in general, like the C programming model is fairly simple. Like this is what everybody starts with. This is easy to debug. Conceptually, it's simple. Indexing is not too bad. But in order to get good performance, you would start calling into vendor-specific intrinsics. So for example, you have like AVX on your x86. You would have a different set of extensions, for example, on ARM. And it's not only that you have CPU-specific code, but you would have to have a vendor-specific code to really get most out of your CPU kernels. In the GPU programming model with something like GLSL, HLSL, and similar languages, you're a bit more limited in terms of what you can express, but the programming model is still fairly simple. I think the most tricky part is that now you have like these multiple levels of nestings where you have threads within your subgroups, you have workgroups, and you are kind of responsible for managing all of this indexing and making sure that you are not only getting the indexing right, but that you're also benefiting from like the memory hierarchy of your device. So for example, you would want your memory access within a single workgroup to be coalesced, so you want it to be kind of all close together. And if you start doing something that's not really suitable for hardware, for example, if you were to read a column of data, you would notice that the performance degrades very quickly. So the key idea of ML compilation is that if you are doing it with these kind of kernel libraries, this gets expensive very quickly in terms of how much effort you need to put into maintaining all of these implementations. The reason is that there's new ML operations that are being invented pretty much on a weekly basis. we have more and more data types. Right now we are down to like FP8, FP6, FP4. And also, if you want to support, more than just one family of devices, you would have somebody who is familiar with the architecture of each device, implementing all of these, ML operations. So we want to kind of put most of the complexity in a shared compiler part, such that, for example, if you want to support a new operations, it will be added somewhere towards the front end, such that the kind of backend code gen doesn't really have to know about this. This is realized in our project called IREE, and our goal is to provide an open source ML compiler and runtime such that we can have ML researchers or ML practitioners, tweaking their Python programs. We can take them and we can efficiently execute them on all of the target devices that we care about. IREE has its own programming model, and we kind of benefit from the inputs being so high level. So our inputs are MLIR programs that very closely model the Python-based frameworks. So for example, we can have high-level operations like matrix multiplication. We can have operations over very large tensor types with dynamic dimensions. And in this case, IREE is responsible for both deciding what goes into each kernel, how to exactly schedule the work, and what to do within kernels. IREE will take care of all of the indexing and distributing the work into work groups, subgroups, and threads. IREE is a part of a larger software stack to make ML deployment really possible. I'm not going to talk about this, but in general, all of what I'm showing here is pretty much open source. IREE is a project under the Linux Foundation. The main kind of framework that we use is MLIR under the LVM Foundation. And then we have two main compilation paths. We have one compilation path for CPU, GPU that includes CUDA and ROCm that goes through the LVM backend. And then we have a separate compilation path for Vulkan that goes through SPIR-V. This also allows us to have support for Metal and other web GPU things that can be translated from SPIR-V to another like GPU format. From 10,000 feet, what we're doing is that we take these Python-based programs, we try to import them into MLIR, and at this level, it's pretty much one-to-one copy of these Python frameworks. And then we have a common representation at the level of IREE. We perform most optimizations, or like we perform high-level optimizations in a target agnostic way. Then as we go down, we kind of specialize the optimizations towards the exact target hardware. And what we produce is a single file compiled ahead of time that contains both the device code and the host code. The device code can be something like an object file for AMD GPU or something like SPIR-V for Vulkan. And we can ship multiple device executables within like a single container file, so that based on what is being actually what is our target device at runtime, we can select the suitable device code, and the host code will be executed by a lightweight VM. So our runtime is very lightweight. It's like in the order of like 30 kilobytes, and it only really interfaces with the driver on your device. So we are not deploying Python. MLIR is like the main kind of piece of infrastructure that allows us to build this compiler stack. It's also open source. It's part of the LVM project. And it's not a compiler by itself. It's a framework for building compilers. The kind of main feature of LVM, of MLIR, is something called dialects. And dialects allow you to define your own intermediate representations, your own kind of small programming languages. These consist of operations, types, interfaces, and attributes. And the core principle of MLIR is that we want to perform gradual lowering. So we want to kind of maintain abstraction for as long as possible and gradually simplify your programs as we compile them. We don't want to go too low level only to have to write analysis to recover the information that we just dropped. One of the dialects supported by MLIR is the SPIR-V dialect. It doesn't go through the LVM SPIR-V backend. It's a separate thing. We support both Vulkan and OpenCL. And it's not a full implementation of the SPIR-V spec. It's mostly on a need basis. So like if somebody needs some op, they can add it. And we also have some custom ops that are really not present in the SPIR-V spec, but they're kind of like nice syntactic sugar that we can use at the level of MLIR. At the end of the day, we serialize the SPIR-V dialect representation into the SPIR-V binaries. And we also have support for deserializing so that we can load SPIR-V binaries and have them represented in MLIR. I have an example of the dot operation on the slides. And you can see that there's some documentation that's being auto-generated. We benefit from MLIR because it gives us, we write the grammar, but it will implement parsing and printing for us. We can define our own verification logic. And we implement interfaces that allow for common compiler analysis and transformations to work on SPIR-V ops without really knowing about the SPIR-V ops. For example, we can say that the dot operation is pure in a sense that something like common subexpression elimination can eliminate it because it knows it doesn't have any side effects. So we start compilation from like a very high-level representation with perfectly nested loops over tensors. So these are like ND arrays with value semantics. These get kind of expanded to a bunch of other dialects. What's interesting is that these dialects can coexist. So it's not strictly a set of lowerings that goes from like one representation to another. You can have multiple representations kind of coexist for some time. Actually, we found SPIR-V to be beneficial to MLIR itself because it allows us to make sure that the higher level dialects have properly defined semantics that are not too closely tied to LVM. So for example, it would be very tempting to say that there's some operation that's defined in terms of LVM semantics, but maybe this would be like an oversimplification. And it came up multiple times that looking at the SPIR-V spec really allowed us to agree on higher level semantics that were more portable. So I have the same sample MLIR program again. And what we would want to do first is to perform target independent optimizations. So for example, here, we can do stuff like if there are, for example, multiple transpositions, we can kind of, we can cancel them out. And we also, at this level, will decide what goes into each dispatch. So dispatch is roughly a kernel at the end of the day. So it's the compiler who decides what the kernels are. For example, here, this is a matrix vector multiplication with some element-wise operation at the end. So we're adding, like, I think, some constant to a matvec. And this would be like one kernel. We could potentially have like multiple matmuls together in a single kernel. And this is really for the compiler to decide. Here I have the same program kind of expanded to the SPIR-V dialect, compiled like all the way down. At this point, it's too long to fit on a screen, but you can see that all of the indexing has already been decided. So we, instead of having a matmul, we have a loop that does some memory accesses and so on. We also decided whether to use shared memory or not use shared memory. And kind of as a kind of side comment, what you'll notice is that actually this representation of SPIR-V is pretty readable. Like when I work on SPIR-V these days, what I often do is that instead of printing it with SPIR-V this from SPIR-V tools, I'll load it to MLIR and read this way because it's just easier to read. So how we go from these high-level programs to low-level programs. MLIR has a bunch of mechanisms to define these kind of fine-grained rewrites. You can say that, oh, I'm going to take my reduction and I'm going to decompose it into a few, for example, additions. So I'm going to do like a tree reduction. Once you have a few rewrites like this, you put them together in a rewrite pattern set. And later, there'll be some like common rewrite driver that can automatically, that has logic to traverse the IR so that you don't have to really worry about how you go around your program, what is really the order of your traversal. You can hand it off to something else that will do it for you. And what you only do is you write very small local transformations. And because we start from like very high level representations, we can maintain perfect loopness and perform aggressive loop optimizations without having to do loop analysis, just because structurally we always maintain the perfectly nested loop form. And we can decide common optimizations, like we can do tiling so that we benefit from various levels of cache. At the end of the day, we can vectorize the code so that we benefit from SIMD vector operations, and so on. And unlike traditional C compilers like GCC or Clang, that only provide you really with a handful of optimization pipelines, like -0.1, -0.3, we have compilation pipelines that are specialized towards these like most important ML operators, like matrix multiplication, convolution, and so on. And also at this level, you see, for example, we have a pipeline that's really specialized towards using the cooperative matrix SPIR-V extension. We encode our kind of heuristic choices around the pipeline we're going to use, tile sizes, and other parameters in the IR as attributes, such that we can do auto-tuning based on that and have something kind of select the optimal knob settings based on the empirical performance on our benchmarks. However, SPIR-V is not a single target. We can have SPIR-V devices that are like full desktop GPUs with the newest feature sets. We can have pretty basic mobile devices like Android phones. It's possible they don't even support dot product instructions. Maybe all is available is like scalar, multiply add. And for this reason, we added support for having multiple variants of SPIR-V executables, being compiled at the same time. And at runtime, we can query the Vulkan runtime and decide which kernel to execute based on the device that we have at hand. Because SPIR-V is not a kernel generator, we are free to decide what is the data format of kernels. So as long as it's not like the input or output of the whole program, we are free to decide what kind of data gets exchanged across kernels. And this allows us to perform arbitrary fusions. We can put 2 or 3 matmos in the same kernel if we want to. We can do transformations like padding to increase the L1 cache bandwidth. And this is an example of something that will be kind of hard to do without either very specialized hardware intrinsics in a kind of like a traditional kernel-based implementation, because it would expect the data that comes in to be in like the format that the library decides. In our case, for example, we can say we're going to add a few columns of data, just that the data in like one row and the data in the next row spans across 2 different cache sets so that we can benefit from the memory bandwidth of loading data from 2 different cache sets at the same time. If we push this idea further, we will get something even more aggressive or even more kind of specialized. And we call this data tiling and microkernels. The idea is that we can pack the data in the exact format that the hardware prefers. So at the end of the day, there'll be some matrix instructions that we want to use for matrix multiplication. These typically have complicated layouts such that you would traditionally have to load them from main memory, you would have to swizzle them, you have to put them in shared memory. And instead of doing that and kind of having this overhead in the matmul kernel, it's possible that we can save the data in the exact format that the device wants in the previous kernel. And when we do matmul, we don't have to worry about any index calculations. We can just load the data and know that it's in the correct format. And it's also possible that the producer of this data is not even kernel that was running on the same GPU. It's possible that, for example, we have a heterogeneous scenario where we're executing on a laptop with an NPU and GPU, and we can ask the GPU to produce the data that the GPU can then use. The difficulty is that this plug and plug has some overhead, and we need to decide when it's worth adding padding and when it's better to just do the simple thing and just do the index calculation inside the kernel. These are typically like once you peel off all of the indexing and you know that the data is in the exact format, writing kernels by hand actually gets much simpler. So we have a hybrid solution for the most important use cases where we want the absolute best performance, where we can implement the innermost matmul loop by hand, take care of all of the exact instruction scheduling so that we get the best instruction sequence that we can, and then we can link it into the whole loop structure generated by the compiler. So it's in a sense the best of both worlds. SPIR-V doesn't have the best story when it comes to languages for kernel development. So what we did instead is we added support for writing kind of low-level SPIR-V kernels in MLIR itself. So we can use the SPIR-V dialect as the layer of intrinsics, and then use higher-level languages that provide us structured control flow or multi-dimensional vectors to perform the computation. So this is available in MLIR upstream, and we also have support for integration tests for these kernels. And I wanted to advertise that even though my talk is focused on IREE and the IREE compiler, because of the SPIR-V support in MLIR, you can build other compilers that target SPIR-V. So for example, there's a GLSL compiler that goes directly to MLIR without using any kind of Clang-like front end. So as a result, I think we succeeded in having a compiler that has very broad device coverage, because it's both CPU targets, GPU targets through CUDA-ROCm, but also a very wide range of other GPU devices that we can support with Vulkan. And this can be kind of tiered in a sense that we can have handwritten kernels for the innermost matmul loop for the most important devices we care about. We can go to cooperative vector for devices that support cooperative matrix. And then we can have some fallback target that just does the simple thing for everything else. And last year we had pretty good performance over some common models like Llama and Stable Diffusion. I'm not presenting the exact benchmark results here, but I claim that we had state-of-the-art performance on some AMD devices in the past, meaning that we had the fastest known implementation at some point in time last year. And in micro benchmarks against kernel libraries, we are competitive in a sense that our code generation is sometimes better, sometimes worse than handwritten kernels. On average, is slightly slower. However, this is not the best comparison for us, just because it forces us to kind of conform to a style of kernels that we don't necessarily prefer. So we really benefit from these inter-dispatch optimizations that we are free to do. We are still working on our story for having heterogeneous executables, such that you can execute, for example, some work on the NPU and offload the remaining work to the GPU. We also have ongoing work on our tuner so that you can take your whole model. You can spend a few hours to just doing search over the various compiler heuristics so that you get your last 10% of performance. And this really matters for data center deployments when you want to deploy a model over, like 50,000 GPUs. We plan to work on microkernel support for GPUs. And we have also an ongoing work for an efficient serving layer so that, you can have a solution where you deploy something like Llama or Stable Diffusion, and you have a server that you can talk to, and it takes care of scheduling the work, batching, stuff like this. Both IREE and MLIR communities are fairly open. All of the source code is on GitHub. We have an active Discord server and discourse forum for MLIR. So you can see that almost all of the discussions happen in the open, and it's fairly easy to engage with us. And now I can take some questions.
So I'm curious, do you guys use MLIR over directly? I mean, the alternative, an alternative would just be bring it to SPIR-V and doing everything in SPIR-V. Is the MLIR convenient because it's a higher level of abstraction, or is it just because of the LLVM framework you get with it?
So the reason, the question is basically, is the alternative going directly to SPIR-V? And the answer is that this would be extremely hard just because of the difference in the level of abstractions of like these Python frameworks and SPIR-V. We would have to pretty much have a library of SPIR-V kernels that we inline. And this won't give us good performance.
So Epic has custom API for AI inference on Unreal Engine. Currently, they are using ONNX runtime to implement the actual inference on device, but it's a bit, I would say, work in progress. It doesn't really support many platforms yet, and it's also, I think it's focused on CPU inference at the moment. So my question is, how easy would it be to integrate this with ONNX runtime, and what kind of work would it take?
So I think there are two aspects to this question. We do have support for ONNX, so as an input format. So that's supported. Separately, how easy it is to integrate IREE into your game engine? I think that's the question. So we have CAPI. Our runtime is very lightweight, so you can create your Vulkan instance on the on the engine side, and give all of the handles to our runtime, and we'll use it. We don't have to initialize the device. We don't have to do this work. The application can do it. And there has been some work on integrations like this. I think the most advanced one that I've seen was somebody in the community adding IREE to Godot. And they had I think they were doing some vision stuff with detecting limbs of characters and stuff. So somebody has attempted something like this. I don't think we have anything out of the box that will work, but in theory, there's nothing that prevents you from having an integration like this.
Okay, thank you.
Any other questions? Yep.
Nice presentation, thank you. So can you comment on whether the work you're doing with MLIR and IREE is complementary to the more the new generation Vulkan extensions like Co-op Matrix 2 that we heard about earlier? Are they on a convergent path, can help each other, or are they diverging?
In general, we can kind of have a tier support for our target devices, so that, for example, we can have in general less overhead. For example, if we do these kind of layout transformations on the producer side instead of in the kernel that uses the data. So, for example, this is something that we would prefer on our top of the line hardware, where we really care about the performance, and we know the layouts, we can assume them. But for something like this, the second tier of support, we would absolutely want to use extensions like cooperative matrix, and this is what we do. We would benefit from reductions in co-op matrix too. I haven't looked at the exact details, but having primitives like this definitely helps.
So, great presentation. I learned a lot. What would you say the performance penalty would be to go straight to SPIR-V and then use another compiler versus going straight to LLVM for a proprietary solution?
Going to SPIR-V versus going to LLVM. So I think this could be like a scenario of, like for example, on our desktop cards, like RDNA, we have support for both, ROCm and Vulkan. So we in the past we did direct comparisons, and at that time the quality of the generated code wasn't that different. However, we saw that we had more API overhead on the ROCm side. So it's not only just the quality of the generated code, it's also the overhead of the API and kind of the granularity of work it expects. How much time it takes to launch a kernel, stuff like this, right? So it wasn't a direct comparison, but at the time we noticed that ROCm had more overhead. So, however, the issue of SPIR-V was that SPIR-V isn't the best at handling like large buffers, like larger than 4 GB. So for larger models, we would use ROCm because this was, we could just use pointers, 64-bit pointers. SPIR-V was better for smaller models, and we started investing into improving the ROCm overhead at the same time. So it's at some point in time, Vulkan was faster for smaller models, but larger models didn't work, and both ROCm and Vulkan could be, improved in a sense that, at the end of the day, it's the same device. We should be able to get to the same level of performance.
Any last questions? In which case, we can thank our speaker and break